Functions are one of the central objects of investigation in mathematics, so understanding how they are expressed and evaluated is of critical importance. Let's quickly review some definitions needed in a discussion of functions. A function is a set of ordered pairs in which no first coordinate is repeated. The domain of a function is the set of first coordinates of the ordered pairs in the relation, and the range of a function is the set of second coordinates of the ordered pairs in the relation. Let's now consider a few examples. The set F1 equaling the ordered pairs A2, B3, C3, and D5 is a function with domain equaling the set of elements A, B, C, and D, and range equaling the set of elements 2, 3, and 5. Notice there is no prohibition on repeating second coordinates in the definition of function. The set F2 of ordered pairs of the form xy, where y equals 2x plus 3, is a function with domain, the interval from negative infinity to infinity, and range, the interval from negative infinity to infinity, since the graph is a line with slope m equal 2. The set F3 of ordered pairs of the form x, y, where y equals x squared plus 3, is a function with domain, the interval from negative infinity to infinity, and range, the interval from 3 to infinity, which is closed at 3 and open at infinity. This is because the graph is an upward parabola with vertex 0, 3. Now we can proceed with an introduction of function notation and related terminology. When a function is defined using a formula or equation using x as the independent or input variable and y as the dependent or output variable, we say that y is a function of x. We write y equal f of x to denote that y is a function of x. Notice f parentheses x is read f of x. The letter f is the name of the function, x is the input variable, and f of x is another name for the output variable y. It's important to notice that f parentheses x does not represent multiplication when f is a function. To evaluate the function y equal f of x at x equal a means to find f of a, the output associated with the input a. To do this, we essentially substitute a into the formula wherever x appears, as we will see in the examples. Let's begin with the doubling and add 3 function. This function can be described by the formula f of x equal 2x plus 3. This formula is specifying the output associated with the input x. We double x and add 3 to get the corresponding output value. Notice that the graph of y equal 2x plus 3 is a line with slope m equal 2, which will pass the vertical line test. Therefore, the formula defines a function. Now we want to evaluate a variety of function values. To evaluate f of 1, we double 1 and add 3, yielding 5. To evaluate f of negative 4, we double negative 4 and add 3 to produce negative 5. Similarly, f of 7 equals 2 times 7 plus 3, or 17. To compute f of a, we double a and add 3. This gives 2a plus 3, which we cannot simplify further because we have unlike terms. Similarly, f of b equals 2b plus 3. Now, to evaluate f of a plus b, we view the quantity a plus b as a single input. We double a plus b and then add 3. This simplifies to 2a plus 2b plus 3. It's very important to note that in general, f of a plus b does not equal f of a plus f of b. Functions do not distribute over addition like multiplication does. Let's compute one more example. Consider the function given by g of x equals 1 over the quantity x plus 8. We will again evaluate a variety of function values. To compute g of 1, we substitute 1 into the formula for x, producing 1 over 9. To compute g of 5, we substitute 5 into the formula for x, producing 1 over 13. Similarly, to compute g of negative 3, we substitute negative 3 into the formula for x, producing 1/5. Correct implementation of the order of operations is critical in these problems. To compute g of negative 10, we substitute negative 10 into the formula for x, producing negative 1/2. Recall that for a fraction, a negative fraction, whether the negative is in the numerator or in the denominator or in front of the fraction, is irrelevant. To compute g of t, we get 1 over t plus 8. Finally, to compute g of x plus 2, we substitute x plus 2 into the formula for x, producing 1 over the quantity x plus 10.